Okay, let us discuss the next problem. This is from Erudov rotation chapter. So this problem is 1.260. Let me make the diagram for the figure and then we'll discuss about the problem. So let us take the diagram first. So there is a wheels, something of wheel kind, and this is mounted on, there is an axle. So this is the axle. Now this is kept on floor. Okay, are you able to see or not? So this is the figure. Now this is kept on some surface. So surface is there. So we have a surface. Now there is a thread that is attached to this point, and this, there is a point by which there is a force F is acting. Now we call this point K. This is called A and this is called B. Now let us read the problem. So this says a uniform solid cylinder A of mass m1. So this is mass m1 and A is basically a solid cylinder. So this is solid cylinder. So this is a solid cylinder. So we have a solid cylinder here. Rotates, can freely rotate about the horizontal axis. So this axis is freely, no friction. It cannot apply any friction. That means this is a free hinge. And rotate about a horizontal axis fixed to a mount B. There is a mount, so they are calling this as a mount. So this wheel is mounted on this and they are calling this as a mount B. So this is a mount B of mass m2. So mass of this is m2, that is given. A continuous horizontal force F, constant horizontal force F is applied to end K. So this force is constant. This is not a variable force. This is given in the problem. This is a constant force applied to end K of a light thread tightly bound on the thread. So this is a thread that is tightly bound on this cylinder. So there is a thread that is tightly bound on the cylinder. So this means if you open the thread, if you will pull the thread, this will roll in this direction. So if you pull the thread, this will roll in this direction because thread will unbound, and if thread will unbound, this will start rotating in this direction. That is given in the problem. The friction between mount and the supporting horizontal plane is assumed to be absent. So this means between mount and this plane friction is absent. Mu is equals to 0. Find the acceleration of point K. So we have to find out first what is the acceleration of point K. So let us say first work for this. So how we'll find acceleration? Now see the point K that is on the thread. So this is the thread point. Now if you see this as a system, so if I assume this is my whole system, so this is my system. So if I say this is my system, so this is my system, this includes this part. So if I assume this is the system, now the external force that F that is acting. So I can find what is the acceleration of the center of mass of this system. And now the same acceleration will have acceleration of axle. So acceleration of center of mass, this means all points. So this means if this simply translates, all point on this mount will have same acceleration, that is the acceleration of center of mass. Now this axle will also have same acceleration of center of mass. But now the thread will have different acceleration. It will be basically rolling. So this will also have an acceleration. So rolling, due to rolling, this point will have an acceleration. So let us call this point will have two acceleration. One is because center of mass is moving, so it will have an acceleration due to center of mass motion. Another is due to, this is rolling, so this will also have alpha times r due to the rolling motion. So I can say any point here, either here or here or here. So let us call this point as P. So point P will basically have two acceleration. Point P will have two acceleration. So acceleration of point P will be acceleration of center of mass of system plus acceleration about center of mass. So this is about cm, acceleration about cm. Now at this point both will have same direction. Acceleration of center of mass is also in this direction. Alpha into r, that is tangential, that is also in this direction. So these two vectors simply can be added scalarly. So acceleration of center of mass is a cm plus acceleration center of mass is alpha times r. Radius of this cylinder should be given in the problem. Even if it is not given, we will find in terms of other forces. I think it should be given. So let us assume this is given. Now let us say find alpha. ACM is very easy to find because total force on this system is F. What is the mass on this system? Force by mass. Mass is m1 plus m2. So this is the acceleration of center of mass of this system. Now finding alpha, we have to consider this wheel. So if I consider this wheel, now in this wheel, this axle will come. There is a tension or there is a force that will come here. Now axle will also apply some force on this. So axle may apply, axle can apply a force in x direction, reaction force. It can also apply a force in y direction, but I am not interested in those forces. If I take torque about point A, let us call this point as Q, center. So if I take torque about Q, so this will be mg will gone, F will gone, so mg even also will fall from this point. So torque of mg is also gone. Since this force passes through Q is also gone, it's also gone. So torque will be simply F times this distance r. And torque is nothing but I alpha. So F times r, this will bond in the roll in this direction. I is, let us say this is a solid cylinder, so mr square by 2 into alpha. Mass of this is given in the problem, this is mass m1. So this becomes F2F by m1r is equals to alpha times alpha. So I need alpha r. So from here alpha r is equals to 2F by m1. So now I can find what is the total acceleration. So you see here, acceleration of point P is ACM plus alpha r, and ACM is nothing but F by m1 plus m2, and alpha r is nothing but 2F by m1. So simple. Now if I take m1, m2 common, m1 into m1 plus m2, so the upper we will have F is common, so I will have m1 here, and here I will have 2m1 plus 2m2. So acceleration of point P is given by this equation, F times 3m1 plus 2m2 divided by, this is m1 into m1 plus m2. If you check, are you getting or not? You can do your calculation here even if you have not got. You must see acceleration of point P is nothing but acceleration of center of mass plus acceleration about center of mass, and I little massage this equation. This is not massaging. People call this massaging equation, but it's something different. So you can find from here what is the acceleration of point P. This is the acceleration of point P. Now any point, not only this is the acceleration of point P, even this is the acceleration of point K, because this is the same. The acceleration of point P, now the acceleration by which this thread gets unbounded is same as the acceleration of point K. So this is also acceleration of point K. If you are not able to understand, think a little, you will get the point. So this is also acceleration of point K. So this is the first part. Now next part says, so you can check your answer. Now next part says, the kinetic energy of the system t second after beginning of the motion. Kinetic energy of system after t second. So you see, now I can apply the work energy theorem. Initially this was going with zero velocity. Initially it had started the motion. So change in kinetic energy is equals to work done by different forces. Work done, total work done. Now initial kinetic energy is 0, so final kinetic energy is half mv square minus 0. That we have to find out. So this is final kinetic energy minus 0, that is simply final kinetic energy, is equals to work done by different forces. Now I can see what is the work done, that is simply force, external force dot ds. And if you see this point F, this has a force and displacement in this direction and force also in this direction. So let us say, consider the point where the force is applied. So if I consider this point, so I have to discuss the displacement of this point. And displacement of this point is same as acceleration of this point into half a t square. So this means displacement of this point is given by ut, initial velocity is 0, acceleration is half a, acceleration of point p into t square. This is simple. You can find displacement of point S, point K, that is S is equals to ut plus half a t square. Acceleration of point P we have already found from part 1, or point K. This is same as acceleration of point P or acceleration of point K. I am interested in acceleration of point K. So half a t square. Now force I know. So kinetic energy final simply force is F. Acceleration we have found, this is acceleration of this. So half a, acceleration is this F into 3m1 plus 2m2 divided by m1 into m1 plus m2 half a t square. So this is the final kinetic energy. 2-3 points is important in this question. Important point is, if I want to find out the total work done, I have to see what is the point where the point of application of force, that is the point K, and I have to find the distance of point of application of force, that is the displacement of point K. If I know the acceleration of point K, I can always find what is the distance traveled by point K, that is S is equals to ut plus half a t square. I know initial acceleration, initial velocity of point K is 0 because the motion has just started from 0 velocity. So S is equals to ut, that is 0 plus half a t square. Acceleration of point P we have already found in the first part of the question. That is the total force divided by total mass. Total force, external force is F. Total mass is m1 plus m2, that is the acceleration of center of mass, plus alpha times r. Alpha is the torque divided by moment of inertia. So from there I can find the acceleration of point K. As soon as I know the acceleration of point K, I can apply the point of application displacement into the force applied on the point of application. You see, in this case theta is equals to 0 degrees, so this becomes simply cos theta becomes 1. So you see, final kinetic energy is this. We can always find. Well, this is a function of time. You see, kinetic energy is a function of time. If you differentiate this kinetic energy, you can find dk by dt. That is also a function of time. So you see, kinetic energy dk by dt, that is positive number. So kinetic energy increasing. Are you getting or not? So if you are applying a constant force, kinetic energy is increasing. That should be, because force is doing work. So where this work is going? This work must be stored in terms of kinetic energy, because there is no change in potential energy. And this kinetic energy increasing with time. dk by dt is positive. We'll discuss the next question. You think about more. This is a good question basically. You see in J there is one question related to the force work done, in which we find out the force at the point of application and we find the displacement at the point of application. This is the only important point we learn in this question. That is, work done is equals to force on point of application into displacement of point of application. We'll discuss the next question.